Okay, so here's where we were last time. Welcome back, everybody. I hope everybody had a nice and relaxing spring break and is ready to hit the ground running. Don't forget, we do have a test coming up just a few days into this week. Okay, so anyway, here we go. We were talking last time about symmetry, and in particular, this is the big theorem that we were making use of. It's extremely powerful. Notice the punchline. The punchline is a double integral, which could be quite a pain to actually compute, is 0, right? So this is a massive, massive punchline, very, very high value conclusion to be able to get, right? And what's the cost? It's so little. You just have to check that the function's odd, right? And check that the domain is symmetric. Now, there's several steps in doing these, right? And we've talked through exactly what those steps are, and we'll talk about that again in a moment. But relatively low cost, massive payoff. So this is one of my favorite theorems in integration. I'll give you the same warnings we talked about last time. You do have to have both conditions. A symmetric domain means nothing, right? Because the integrand might not be odd. In fact, what are the odds? I mean, most of the time your integrand's not odd, right? So just a symmetric domain just doesn't cut it. And likewise, you have to use the same line for both of these requirements. And also very important, it does not work otherwise. Okay, so a bunch of stuff we talked about, and then I noted that to have a complete symmetry argument, right? And keep in mind, it's not a class about answers, it's a class about reasoning, right? So you got to give me your reason, you got to give me the argument, explain your thought process. Here are the 5 points that I consider to be essential to a complete symmetry argument. You got to tell me what line you're using, right? I need to know what the formula for the reflection is, because that's going to be necessary. Once you claim that the function is odd, you're going to need the formula for the reflection to demonstrate that the function is odd, right? And these things are usually not obvious. Sometimes they're easy to anticipate. Sometimes they, have seemingly all the earmarks of, a function that does what we want it to. Needs to be shown. Okay. And then lastly, you of course also have to make it clear that the domain is symmetric. This I do not require demonstrations. It's usually the case that if it's true, then it's usually pretty clear. Right? So no justification necessary there, but you do have to be correct in that assertion. Right? This leads me to this warning that I gave you last time, which is you do have to be careful using symmetry. It's very tempting, it's very alluring because you get this awesome sort of get all this conclusion out of relatively little effort. Everybody wants to use symmetry if they possibly can, but if something in the argument fails. Right? If there actually, in fact, is no symmetry argument, then any claims about there being a symmetry argument is just wrong. Even if part of the argument is correct. Yeah, but it's part of an argument that goes to a dead end. It does not represent any progress on the actual question that was asked. Right? So I warn you, I beg you, please be careful. Please double check, triple check, and make sure that the symmetry argument is valid before you use it. Okay, so that's where we left off at the last example I just skipped over. Here we go, new turf. So here's a domain drawn right here. It's bounded by certain curves that we can write down, given. And the question is to compute this integral defined on that domain. So you can slice and dice, and that's going to be a lot of work. You're going to have to break it up into 3 separate pieces, no matter which way you slice. Right? So that's suboptimal. So the much easier way is to use a symmetry argument. I'm going to look at this picture. And it just kind of leaps off the page at me that this domain is symmetric over that line. Now, again, I'm not going to demonstrate it. I think it's clear. These lines here, for example, are clearly their own reflections. There is some algebra we could write down. You don't have to. I don't think it's necessary. And then, furthermore, this curve is its own reflection, or maybe we might want to say these two curves. Anyway, say that however you like. But clearly, each one of these pieces of that curve reflects into the other one. So we have ourselves a line of symmetry. So there's the line of symmetry. Here's my formula for reflection. Now let's talk about this formula for reflection here, and I'll do this in purple. How do I know that that's how you reflect over that line? Well, here's the reflection, right? And you can just literally take an arbitrary point, call it x comma y. You can see where x and y are in this picture. That's your x, that's your y. And then you can just straight up see what happens when you reflect that over the given green line here. I guess I'd better. There we go. When you reflect this dark blue little rectangular frame over the green line, then now you get this charcoal gray rectangular frame. And just kind of looking at which distances or what distances, which ones positive became negative, et cetera, you can just straight up see this formula for the reflection. How are we doing on that? Does everybody buy it? This is a nice trick, by the way. I'm a big fan. If you don't draw the rectangular frames, then one could argue that, trying to figure out, where is this reflected point, is not immediately clear, because it's not clear how angled lines reflect. That's not obvious, right? But it's very easy to see how rectangularly sort of, if you're reflecting over a 45-degree line, there's just some nice lucky breaks there, and it's pretty clear that that reflects into this. Okay, so nice trick. I hope that'll be useful. Okay, proceeding. Domain symmetric, right? There's the required. Now, I gave some text here in case anyone else is, if you're curious, how do I know what led me to believe that the domain is symmetric? That's for that purpose, but you're not required to give any of this justification of the symmetry of the domain. Okay, how do I know my integrand is odd? This is, you got to be careful with it. And again, it's tempting to say, I see odd exponents, so I guess that means it's odd. That's not true, right? It's very important that the reflection itself has to factor in to this discussion of why that function is odd. Keep in mind, there's different kinds of odd. There's odd over different lines. Over some lines, this function is not odd. In fact, over most lines, this function is not odd. Right, so we need to know specifically that it is odd over this line for which this is the reflection. So we have to actually plug that in as such. We got to take this formula for the reflection, right? Plug that into our F, and be careful along the way. So again, easy to kind of get confused. Keep in mind when I say negative y is our first component that we're plugging into the function, that means negative y goes into the place where x was. Right? I hope that makes sense for everybody. If this weirds you out, there's a simple way to avoid this problem. No problem at all. All you got to do to avoid this, arguably a confusion of variables that I've created here, is to just rewrite your reflection in terms of different dummy variables. Whatever. Right? Just rewrite in terms of different dummy variables. Now there is no confusion of variables at all. So suit yourself on that. Doesn't matter. And then, algebra ensues, and it's, you gotta be careful with the algebra. Obviously, there's lots of places where one little sign error can mess it all up, right? So be careful with that. Nice punchline, though, as required, the reflection going into the function results in a minus sign. A minus sign. Oh, come on, man. This stylus, I gotta get a new stylus. This minus sign coming out of the function. That's what it means for a function to be odd. And we're done here. Integral 0 by symmetry. Is everybody happy with that? It's really awesome. Result saves us loads of effort. Okay. All right. Now, here's a dangerous example. Very dangerous. And I hinted at the warning about this previously. And that is that you got to be really careful. Symmetry arguments are delicate, and there are dramatic risks, right? These are landmine problems. They can be landmine problems, right? So, look, here's what a student moving just a little too fast and loose might look at this triangle and say, ooh, check it out. I see a 1 and a -1. Those are reflections of each other. I see a bunch of zeros. Everybody loves zeros. This, just from the numbers, looks like it might, I don't know, maybe, might be symmetric. And good news, it is symmetric. Let's look at this integral that we've been asked to compute. We look specifically at the integrand. Hey, it has an odd exponent. This function is odd. I have a symmetric domain and an odd integrand. It is so tempting to say, wave the magic wand of the symmetry theorem and say, poof, the integral is 0. It doesn't work. These are symmetric over different lines. Right? So, yes, this domain is symmetric, indeed, but it's over the y-axis and only over the y-axis. Right? Yes, this function is odd, true, but only over the x-axis. So there is no symmetry argument here at all. No such thing. Everybody see what I'm talking about? Dangerous question. So, heads up, be careful. This is part of the reason that I want to see the whole argument. It's not the only reason. But let's say it this way. One of the silver linings of requiring that you give me the full argument is that will cause you to uncover what otherwise would have been a catastrophe on this question. What do you think? Everybody all right? All right. Okay. Let's talk about 3 dimensions. It's extremely similar. The main difference between symmetry in 3 dimensions and symmetry in 2 dimensions is that what a reflection is, it takes a slightly different meaning. I mean, it's highly analogous and it's highly relatable. Right? Reflection is just now through a plane. And frankly, this picture right here, and talking about reflections through a plane, is the more relatable notion of reflection. Again, every time you look in a mirror, right? The surface of the mirror is a plane. Right? The reflection that you find yourself looking at is there when you are here. Right? This is as a relatable notion of reflection as there is. So no hard concept there, I hope. And we define oddness the same way. Oddness means that reflection in gives a minus sign out. Ditto what it means for a domain to be symmetric. I need the region to be its own reflection. Say that however you like. We get the with the erasing. Okay. We get the exactly expected theorem. Notice it looks at a glance literally exactly, right? Like the previous theorem. The only difference is that here I'm talking about a triple integral, and the reflections are over planes instead of lines. But I mean, it's the same exact concept. And I deliberately wrote it on the page, laid out exactly the same way, right, to emphasize that analogy. Same warnings. You got to have both conditions be satisfied. You got to use the same, plane instead of line, but same symmetry, right, for both of the necessary symmetries. And the use, again, it's the same. It's so similar. So here's an integral. Suppose we are interested in the unit ball, right? And I want to compute, for whatever reason, I want to compute this integral. And by the way, I'm having my own personal flashbacks to my physics classes that I took way back when. And these can be nightmares. Massive nightmares because, if you do a rectangular integration on a ball, there's square roots all inside your bounds, which means that there's square roots all inside of your, 2 of the 3 integrals that you need to compute. Square roots everywhere, right? It's horrible, right? Completely not suggested, I understand, by the integrand that you actually see. That's not your integrand for your second and third, for your second and outside integrals, right? Those integrals have integrands with square roots just everywhere. So this is a nightmare of a question, except for the fact that we can make a symmetry argument. Here's the symmetry argument I'm going to make. I'm going to talk through some of the details after instead of before. So forgive me for arguably being out of order. I'm going to use this plane as my plane of symmetry. Again, I'll tell you why in a moment. Reflection through this plane has this formula, a little geometry exercise to think through. Make sure you're comfortable, by the way, with why that is. If you're not comfortable, come talk to me. Be happy to, draw pictures and elaborate. But of course, balls are symmetric about every plane going through the origin, right? So that's an easy pitch, I hope. And why is the function odd? Well, because, again, when I take this reflection, when I plug in the reflection, the result of plugging in the reflection is this minus sign on the output. So we're done here. This integral is 0 by symmetry. We walk away. We take a sigh of relief that, oh my gosh, I almost had to compute some horrifying integrals. Thank God I didn't have to actually follow through and do those integrals. Natural next question, though, where did I come up with? Why did I decide the XY plane? Right? Did I just pull this out of thin air? What led me to make this choice? And in fact, I reverse engineered it. And this is a good exercise. This is a good skill to think about. I knew that I was going to need for my function to be odd. So I looked at this integrand and thought, okay, what's going to make this odd? Algebraically, what do I need to make this actually play through, right? And, of course, what occurs to you, very first thing that jumps out at you when you're looking at this function is you see that 3. I have exactly one odd exponent in this case. Wouldn't it be nice if my reflection just turns z into negative z? Because then that minus sign gets cubed and it comes right out and boom, there's my minus sign, big victory, right? So the reasoning goes like this. This odd power motivates that I want this formula for reflection. That was my thought process, right, when I started working this question out. And then I had to further think, all right, just because I want this to be a reflection doesn't mean it actually is a reflection. Then I have to start thinking geometrically, is this formula here actually a reflection through some plane? And, well, you think about the geometry, right, but that motivates that this should be our plane. So we're literally reverse engineering the argument, right? So that all of that I just explained, you don't have to write down. Right? But what you actually do write down is just sort of the forward motion through this reverse argument. Namely, I pick this plane, that gives me this reflection I plug in and get that this is odd. Does everybody follow that thought process? So I encourage you to think strategically, right? When you're looking at an integrand, ask yourself the question, what do I got to do, right, to make this integrand odd? Is anything leap out at me? Any sort of obvious choices? And if so, let that guide you. Okay. All right. Cool. Okay, that's 5.5. Finally. Right? When it takes us 4 days to get through section 5.5, it's brutal. So moving on now to 5.6, there's a couple of applications in here. I'm going to go kind of quickly through this stuff because it's applications. A lot of what we're going to do here is actually physics and or engineering, and I'm going to do just enough of physics and engineering to give us an excuse to do the math, right? But I don't really want to focus on learning engineering here. That's the engineering class's job, right? That's not our job. Okay, so first I want to talk about a concept called the average of a collection of numbers with repetitions. We're going to motivate something called a weighted average. So, reminder, if you want to average a bunch of numbers, here's how you do it. Right, you add them all up, you divide by the number of numbers. No big deal. I'm going to rewrite that like this. All I did is rewrite the 6 in the denominator. Notice that the number of numbers in the numerator is the same as the number of ones in the denominator. Okay. Then I can group kind of like this, if you will. And each one of these groups I can kind of rewrite as I've done here, and this gives me a streamlined formula for how to compute the average that I started off with in the first place. Right? I mean, this formula here, there's nothing wrong with it, but this is a little bit streamlined. Right? And notice what this does is this kind of streamlines the process of having repeated numbers in your average. Right? And in particular then, let's see, let me get my colors right. This number here is a representation of how many times that number counts. How many repetitions are there of it? Right? You can see likewise over here, this number here is an indication of how many times I counted the 8. Right? So I'm going to rewrite then this whole expression like that. It's just using sigma notation. That's for streamlining purposes. And this is called a weighted average. Weighted comes from kind of a reinterpretation of what we mean by repeated, right? If 4 appears twice, we're counting it twice. We are, in some sense, then thinking of the weight of 4 in the average as being 2. It's a different point of view on it. Everybody all right with that? Okay. And by the way, I mean, my motivating example here, of course, we're talking about the number of times a value appears, in an average. That makes it sound like it's an integer, but notice that once we rewrite it as algebra, there's no reason why the weights have to be integers. Right? We can literally think of them as being just how much impact we want these numbers to have on the average. And Okay, so a calculation that y'all might find relevant, possibly even familiar, is let's talk about course averages, right? And in our course, your course grade is going to be computed by based on a course average that is literally a weighted average. We talked through, now these numbers here aren't the correct weights for our class. I didn't want the numbers to get kind of mucky with counting in, in this class we're doing homework counts a little bit and attendance counts a little bit, right? But just to keep it simple, in this hypothetical class we have these weights right here, which you see right there in the formula, right where they're supposed to be. Right? The numbers that we're averaging, right? What we want to find the average of are these values. These are the grades that Bob got on the exams. Notice that those are right there where they're supposed to be. Right? This is just plugging in to the weighted average, and you can see then what Bob's grade in the class is going to be. Bob gets Bob's weighted average is this number right here. And now again, hypothetically, if we transition to thinking about our course, remember that there are bins, right? And this value, this course average right here, would fall into the B bin because it's between 2.85 and 3.15, I guess, if I remember correctly. Don't hold me to it. I think that's right. But anyway, Bob gets a B in this class. Does that make sense to everybody? Okay. All right. So, all right. Well, there's different things that you can do with weighted averages. And another is to talk about the average value of a function. And now this is weirder because, in high school notions of average, you're averaging a finite list of things. On the other hand, a function defined on an entire interval takes on infinitely many values. Right? So that's a little bit weird to think about. And here's the idea. Let me draw a quick picture here. If you have if your function looks kind of like, let's say, like that. Right? One could argue that, okay, well, the function takes on all the values here between sort of there and there. There's a lot of values that the function takes. What do I just average these numbers? No. That doesn't represent the fact that this function apparently takes these values down here over a much wider range, in my interval, in my domain here, right? Whereas these values up here, there's a much narrower set of input values. So, said differently, this blue function is in the green range more often than it is in the purple range. Right? So I should count these green output values more. I should give them more weight in the average. So the way we represent this is we use size in the domain as the weights. Right? So dx is our weights. And then we just keep in mind what we're trying to find the average value of is this function f. So we're looking at the output values of the function, using size in the domain as the weights, and copying from our previous discussion. This is what the average value of the function ought to be. With that, based on that point of view. And now it's just a matter of computing. Notice a quick rewrite we can make is this, based on the fact that this denominator is always b minus a. That's nice, right? Very convenient. So it's a convenient simplification. And here we go. Here's an example. Suppose you want to know the average value of sine x on sort of one, what do you call it? Hill, right? One lobe. I don't know. One chunk, right? What is the average value of sine x? And so, fine, no problem. This gives me my denominator there, a pi. Then I have to integrate the function itself on the given interval, and a little calculus, bam, there's our answer, average value of the function. What do you think? Is everybody with me so far still? Okay, cool. All right. So, same concept if you have a function of two variables. Same idea. It's just we're going to use size in the domain as our weights. That's all it is. It's just that now, because I'm looking in two dimensions, this is a function of two variables, size is now area instead of length. Everything else is morally equivalent. Again, the denominator simplifies. That's a nice little convenience. You might as well. Let's do an example. Let's find the average value of this function x squared, which goes there, per that. Let's see, we're doing this on the unit disk. Let's see, I didn't do that well. The unit disk is my domain. Conveniently, we already know the area of the unit disk. That area is pi. All right, is everybody with me? So just plugging into our formula, and out comes apparently this integral I need to compute. And so now there's a bunch of details, polar coordinates and all that. Make sure that you're comfortable with the reasoning here. Do notice, and I just like to make this plug whenever I can, RD theta, don't forget that stretching factor. Massively, massively important. Real easy to mess that up. But other than that, I mean, everything, it's just a straight up polar coordinates integral, and apparently the answer ends up being a fourth, which is, how about that? Everybody okay? Okay, so a little bit of physics and engineering. Center of mass. Y'all have all heard this idea, center of mass. What does it mean? There's different points of view you can take, some of which are physics-oriented. I'm going to take the mathematical point of view on this at least first, and that is center of mass. It's a weighted average of position. And I think that tracks. I think that's intuitively satisfying for what we mean by center of mass. So literally then, weighted average, right? Here's our formula for a weighted average. And obviously we're going to use the weights, the masses as the weights. Right? So weighted average of position, right? The positions are x1 and x2. Literally weighted average of position. All right with everybody? So, again, a formula. Now, just from a real quick physics point of view, engineering point of view on this, and arguably a good point of view if you aren't satisfied with the idea of just declaring this as both the definition and the motivation for this concept. Nice fact about it, it's the balance point. Center of mass is the balance point for this pair of masses. In other words, if there were given that you have a mass here, and if they were connected by a thin massless support, this center of mass formula, this is where you would put your finger to have it balance, not fall over in either way. So in other words, the torque pulling to the right, the torque pulling it to the left, exactly the same. That's another little exercise. Again, that's physics and engineering. That's not our job here. But if you're curious, it's a nice little exercise to persuade yourself that that works. Okay. So, here's the same concept. Instead of two masses, if you have a continuum, a distribution of mass, if you're in multiple dimensions, so your location, your position is not just an x coordinate. If your position is a point in space, right? Same concept gives this formula right here. Again, the denominator simplifies very nicely, and so most people operate with this as the formula. Okay. And real quick, I want to confess, I write this down recognizing that technically we haven't defined integral of a vector valued function. It's not that big a deal. If you have a vector valued function, you look at everything that's involved in integration. You're adding a bunch of stuff up. You're scalar multiplying. All of that gets done one coordinate at a time. And so I claim that you can compute the coordinates separately. And so you'll see this 1 over m, sure, in all of the coordinates. And then this integral, you can compute the first coordinate, the second coordinate, et cetera, down to, and then the last coordinate. These separate scalar integrals are just the individual coordinate calculations. Okay. Everybody on board? All right, let's get our hands dirty. Let's do one. My domain is this upper half disk right here. So I have, let's say, maybe this is a sheet of metal where the alloy varies, and so it's more dense on the left, less dense on the right. I don't know, whatever. Then radius A. Oh, now we are further indicating though that density is constant, so that's going to make our lives easier. So that's going to keep my integrand a little nicer. And let's see, the x-coordinate of the centroid, well, per the formula we just wrote down, here it is. This is the integral to compute, to find the x-coordinate of the centroid. Now, I claim it's equal to 0 by symmetry. I told you these symmetry arguments come up a lot, right? This kind of thing, again, flashbacks to my undergraduate physics days, right? This is a very regular occurrence to find yourself with an integral that, again, with the square roots, because we're talking about a disk here, so that this is an annoying calculation, right, that I can completely bypass with a symmetry argument. And I'm going to leave those details as an exercise for y'all. Make sure to think that through, all 5 of the steps, slowly and carefully, right? You don't want to step on any landmines here. But this integral is 0, and that's nice. Now, related to this symmetry argument, some people will make a physics argument. And in a physics class, that's okay. But the physics argument of, well, I mean, it's symmetric, so the torques on either side of this line must be the same, and so that means the center of mass must be on this line, and therefore x bar must be 0. That's a physics argument. This is not a physics class. So I don't think it's appropriate to make physics arguments when that's not the material being tested. So make sure to give me a mathematical symmetry argument. Right? Make sure to give me the 5 mathematical points that we talked about before. Does everybody see the distinction there? So your argument can't talk about forces and torques and stuff like that. Your argument needs to be addressing the integral and how you understand the integral itself mathematically. Okay. All right. Now here's where it gets a little bit more involved. Here's where we have to really get our figures dirty. The y-coordinate of the centroid, this formula. No symmetry argument. Symmetry argument would not work here. Again, landmine. Right? Heads up, don't step on that landmine. It's very tempting to say, ooh, my domain has loads of symmetries. My integrand has an odd exponent, and you see daylight at the end of the tunnel, and you run for the daylight, and you step on the landmine. Right? So heads up, don't make that mistake. And again, if you think through the details slowly and carefully, you'll see that the details do not hold here. So we cannot make a symmetry argument. But we can talk about the area pretty conveniently, whichever way you want to slice. Notice I've written down 2 different representations of this with my differentials in opposite orders. This is all early chapter 5 stuff, so I'm not going to talk through the slicing and dicing, but this is what you end up with. My integrand, of course, is just y per the formula. And now we have to decide which one of these expressions would I rather compute. And they're going to give you the same answer either way. It doesn't really matter. Suit yourself, right? But I am going to insert here again, in the hopes of, showing you some little, tips and tricks to make your life easier. There is a pretty clear preference for me as to which one of these I'd rather compute. And it might not be the one that you think. So let me walk you through the temptation. First, I'm going to give you a bad point of view, not thinking enough chess moves ahead in the game. It's tempting to look at this and think, oh, I love it when my integrand is a constant. Right? If I put the dx on the inside, then my y integrand is a constant, and that makes the first integral easier. How are you going to beat integrating a constant for desirable of a way to go? And okay, sure, you can do that. But look at this. Here, still easy integral. Slightly, okay, there's a power rule thing. Come on, it's not that bad. But the payoff is massive. If you do the dy integral on the inside, the antiderivative has a y squared in it. That square will cancel with this square root, and all your square roots go away. That's really nice. Does everybody see the point there? Very nice. Even though it makes your integrand arguably a little harder in the sense that you end up with a square, right? Nevertheless, it's a square that's a good thing by killing the square root. So anyway, I'm not saying this is always going to happen, but I'm saying this does happen sometimes, and it's a good thing to keep an eye out for, and hope you'll find that useful. Again, either way, doesn't matter. Either way, you're still going to get the same answer. Okay, now a little bit of physics, and there's just no way around it. We're going to have to do a little bit of physics to be able to get to the math that I want to be able to do. I emphasize, though, the physics that we're going to talk about here is physics in service of math. This is not a physics course. I'm slightly partial to some of the physics, but our goal here is not to do physics. Okay, here we go. I hope y'all all remember this old formula from high school geometry. The arc lengths relate to angles in this way on a circle. Hope that's all good news or familiar. Now let's take a time derivative of both. Right? And taking a time derivative of position, well, let's say it this way. Taking a time derivative of distance, I should say. Time derivative of distance is speed. So, what should we call this thing over here? It's not a time derivative of distance. It's a time derivative of angle. And so it's kind of like a speed in the sense that we're taking a derivative of something that's telling me where I am, right? And you can think of distance as a way of keeping track of where you are on the circle, but angle is just a different way to keep track of where you are on the circle. Taking a time derivative of a coordinate, right? I mean, you'd want to kind of use the word speed, but because it's an angle, we call it angular speed, instead of what you might call linear speed or distance speed or, something along those lines. Okay. Is everybody okay with that? So that's my motivation for why we call this angular speed. And by the way, this is the notation for it. It's the Greek letter omega, lowercase. Okay. All right. So now here's the problem that we're going to address. Let's suppose that I have a large mass. Not just a single point, right? But I have a large mass, and that large mass is rotating around an axis like this. And let's talk about how much kinetic energy is there in that motion, right? Kinetic energy, by the way, again, if you haven't had physics, if you're not familiar with kinetic energy, it's just a way of keeping track of, in a way, how much. It's a pretty fundamental thing, so it's hard to. Anyway, it's how much work you've put into making something move is one way to think about it. Okay, so how would we compute this kinetic energy? Temptation. And again, if you haven't had a physics class, don't worry about it, but this is the standard formula for kinetic energy, 1/2 mv squared. Again, probably familiar to most of you. Here's the problem. This formula assumes that the velocity is constant, that all pieces of your mass are moving at the same speed. And in this story up here, they're not. In this story up here, this little piece of mass right there, in the time it takes for me to do one revolution, I better switch to the pencil. This little piece of mass, in the time that it takes to do one revolution, only travels that far, whereas this little piece of mass way out here, oh my gosh, that, in the time that it takes to do one revolution, travels a much greater distance. That orange particle is literally moving faster than the green one. So which speed do I use, right? 1/2 mv squared, which v? All the v's are different for every particle in this entire blob. Everybody see the problem? Okay, so this is the physics that I need to be able to get to one of the things that I want to talk about here, which is this is a great excuse for me to show you a cool Riemann sum. And there's a temptation to think of Riemann sums as computing physical things, but they don't have to be. And in fact, we're going to use a Riemann sum here to compute kinetic energy. And I'm going to argue, let's see if I guess I'll better zoom out for this first bit. I'm going to argue that on this blob, great big thing, the grand total kinetic energy, well, I can just look at one piece at a time. Right? I can talk about how much kinetic energy that one piece has, and the grand total kinetic energy is the sum of all of those little pieces of kinetic energy that you get by looking at one little particle at a time. Right? Whole is the sum of the parts. And so we have ourselves an integral. This is a triple integral because this is a three-dimensional blob here. And then at that point, well, a lot of stuff works out really well. Let's see here. In fact, on each little piece, how much kinetic energy is on a little piece? Oh, well, 1/2 mv squared. On this one little piece by itself, there is a well-defined speed. There's no problem. The speed, well, it's whatever it is. Right? The speed is, it depends on the radius, and boom. So then all that remains is a little bit of algebraic play. Notice that speed is radius times angular speed. And angular speed is a constant because, well, to be fair, all the pieces are moving at different speeds, but they better be going at the same angular rate, otherwise the blob rips apart. Right? So the angular speed is a constant. You can factor constants outside of integrals. Right? Likewise, you can factor this 1/2 outside of the integral. Right? And all we're left with then is this formula here, which I'm going to rewrite as this formula here. Notice all I've done is I've taken this thing, which I don't know what it is, and I'm just replacing it with the letter I. We'll talk about why I'm renaming that as I in just a moment, but anyway, I'm just going to call that thing I. Look at this weird little coincidence that has happened. Kinetic energy, this formula, looks an awful lot like this formula here. Structurally, very analogous. Right? So in particular, this thing here, right, that's speed. Well, okay, it's not speed exactly, but it's the angular analog of speed. Right? It's kind of like speed, just in an angular sense. And so that gives a motivation for how to interpret this I. This I is playing a role kind of like mass. In the formula, it's literally in the place where mass would have been. And so we're going to say that this thing I is an angular analog of mass. And that's the intuition I want to leave y'all with on what is this thing that I've called I. It is an angular analog of mass. And again, that's just a shorthand for this formula, so that's the formula for it. The name is moment of inertia. And neat tool when you're doing physics or engineering that a lot of y'all are going to be doing. Moment of inertia is a very useful concept. For example, if you want to keep track of, you're trying to improve gas mileage on a car, right? And it takes a certain amount of energy to get the car moving. How can we cut down on the amount of energy it takes to get a car moving? One easy answer is let's get the mass as low as possible, right? It's a lot harder to move some massive, huge SUV, right, than it does to move a Prius, right? But here's another answer. Angular kinetic energy of the wheels. They're spinning really fast. They're kind of heavy. It's very significant, right? And so, how would we minimize that energy? We want the energy to be as low as possible, so the car to be as efficient as possible. Talking about this angular kinetic energy here, for which moment of inertia is extremely relevant, right? It's going to be part of that conversation. And there's a tremendous amount to say about it, and it's, there's other considerations, of course, on how you design wheels, but part of that conversation. Very natural, very physically relevant. Everybody good? Okay, so let's compute some. Let's see here. Again, keeping in mind that this is our formula. That's our formula for energy. This is our formula for moment of inertia. And the first thing I want to talk about, though, is this use of R. And I cringe. arguably R is a polar coordinate, a cylindrical coordinate. Is that what R is in this case? Well, no. R in this case is it's a different radius of it's not necessarily the usual cylindrical R. Right? So I apologize for that, but this is just very standard notation to use, but heads up, it's not the usual polar or cylindrical coordinate. Sometimes it is, but sometimes it isn't. If you're talking about a rotation around the z-axis, and you're looking at little pieces of mass like this one, inside of this large blob, what is the distance to the axis of rotation? Well, distance to a line, of course, right angle and all that. But in that case, yeah, sure enough, it is literally the cylindrical coordinate R. We got lucky on that one. Right? But notice it's just not always. So if you're rotating around this line defined by certain values of y and z, this is a line parallel to the x-axis then, right? If you're rotating around that line, and again, you're looking at a little piece of mass here, and you're wanting to talk about how that rotates around that line, right? Well, my distance is certainly not the cylindrical coordinate. And I'm going to have to think through some geometry to actually compute what this R is at this point. And in particular, notice that we can draw. Let's see here. I'll do it like this. We can draw this little triangle like that, right? And keep in mind the purple line is parallel to the x-axis. That means that this triangle is kind of parallel to the YZ plane. Right triangles. Think about the coordinates, etc., etc. And our formula for R in this case ends up being that. So it's going to be different in every example. What it always is this distance from your arbitrary point in your mass to the line that you're rotating around. Everybody on board? Various other examples that you can look through. Oh, and I'm sorry, I realize now I'm out of time. Okay, I guess I better draw the line right there. Sorry to go over. Welcome back. Good to have you back. And hope everybody had a good break. And see you later. Have a good one.